Now we're looking at another beam. The first one we did, the load was at the middle. Now the load is not at middle because the span of the beam is 9 meters now, and the load is at the point 5 meters from point A. Now let us look at how we're going to deal with this. We're moving on gradually so that people will understand how bending moment is taken. Now, to take this bending moment here, we can start. Let's get reaction A. To get reaction A, I should take moment about support B. Total moment about support B. Total moment about support B is equal to 0. Total moment about support B is equal to 0. I take moment about support B. Total moment about support B is equal to 0. So, because the type of support, these two supports, either A or B, does not resist bending moment. So any moment about them should be equal to 0. So if that's the case, the first force, I'm starting from A now, reaction A. So it will be 9 times reaction A, because the distance of reaction A from B is 9. 9 times reaction A to make reaction A a moment. So I decide to say it is positive because reaction A will turn this way. I decided to call it positive. Then the force 5 will turn against it. So that's minus 5, because since 5 is 5 meters from A, that means it will be 4 meters from B. So times 4. There's no other force. Reaction B will not develop moment at its position because there's no distance from its position. So it's equal to 0. That means RA is equal to 5 times 4 divided by 9. 5 times 4 divided by 9. That means 2.22 kilonewton. Simple. As simple as that. To get reaction B, we take moment about support A, which is equal to 0. That means 9 RB. 9 RB, because the distance of RB from A is 9. Turn this way. About RB, 5 will turn against it. Minus 5 times 5 this time, because we're taking moment out, as at reaction A is equal to 0. That implies that RB is equal to 5 times 5 over 9. 5 times 5 over 9, which is equal to 2.78 kilonewton. So, as simple as that, we have gotten the reaction. So the next thing we do now is to get the bending moment. To get the bending moment in the beam structure. To get the bending moment in the beam structure. So if we can get the bending moment in the beam structure, we have gotten what we want. If we want to design this beam, we design it using that value of bending moment and shear force. So to get the bending moment, anywhere I like, I take bending moment. I can take bending moment at point 1, point 2, point 3. If I want to take it at point 5, which is the one, because that's where I want to check that way it can give me anything maximum. So bending moment at A will be equal to 0. The support there doesn't resist bending moment. At MA is equal to 0. Moment at support A is equal to 0. Then we now move at that point, that is point E. The moment that, well, let's say I can call it C as I called before. So at that at C, turning this way will be at this point. I'm at C.
turning this way, I call it positive as I said. Then the reaction A will be against it, which will be negative, minus 2.22 times 5. So is equal to 0. For that point C to be in equilibrium, which implies that MC is equal to 2.22 times 5. Is equal to MC is equal to 2.22 times 5, which is 11.1, is equal to 11.1 kilonewton meter, because that's the unit of moment. Kilonewton meter. Moment, force, and distance. Kilonewton meter. So I've got the bending moment at that point. Bending moment at B. Bending moment at B will be bending moment at B if it's taken as positive. Then minus the RA 2.22 times 9. That's the distance of A from B. Then that is B is turning this way. RA is turning against it. 5 is turning with it, so plus 5 times this time. We're taking moment 5 times 4. 5 times 4. I'll give you equal to 0. So that's the bending moment at B. So that is that. Now I can draw the bending moment diagram. I draw the bending moment diagram. This is the beam. I draw the diagram. I'll see that at point A, bending moment is 0. Look at it here. Point A, bending moment is 0. At C somewhere here, bending moment is 11.1. It's a linear graph. Look at it like this. This is 11.1 kilonewton meter positive. That's the bending moment diagram. That's the bending moment diagram. Then shear force diagram. I have to get the shear force diagram. This is the structure as well. Shear force at A will be reaction A. And reaction A is, because that's the only force, algebraic summation of forces at that point. The only force is reaction A. If I take it as positive, I have 2.22 kilonewton. That is the shear force here. There's no other load until it gets to point C. At point C, 5 subtracts 2.22, because 2.22 positive minus 5. That will give you a minus. That will give you 2.88, 2.78. Give you 2.78. So 2.22. So this will be higher. This will be longer than this, because this is 2.22. Then this is 2.7. This is 2.78. So on getting here, on getting to the point B, then the 2.78 now, this is positive, which is now negative, minus 2.78, meets up another 2.78, which is the reaction. That means minus 2.78 plus 2.78. It closes at 0 here. So this is negative. This is the shear force diagram. What is here is 2.78 kilonewton. This is the shear force diagram. This is the shear force diagram. With this, we have gotten the bending moment, gotten shear force, gotten reactions, and we can design the beam if you want to design it. That's design the beam structurally, trying to get dimensions that will make the beam be able to carry the load. So it's one way to design it, but now we're dealing with analysis. Now, so we have just gotten this. We will go to another beam now. Thank you very much.